Alright, so yesterday this is where I left off, and so the reason I left off is because I wanted to give you guys these sheets so you can have in front of you, so when we start working these problems, they're right there. So the thing on the board is a little different than what you have in front of you. These are more in-depth, these are more specific, and I'm telling you today is going to be kind of weird as far as setting this stuff up, and you're going to see why you have to set these things up the way that you're going to set them up in just a little bit. And I'm going to go ahead and tell you now that yes, you will be tested on this in this chapter. However, when we get to electrochem, probably right before Christmas is the last topic we'll do before Christmas, this is going to be a major component of electrochem. So seeing it twice will definitely build your foundation and build your skills so you're ready to go once you get to electrochem and understanding how to look at it from both perspectives, okay? So what this is called is setting up half reactions. Okay, so let's look at the sheet, not really necessarily pay attention to what's on the board. Some of it's the same, but some of it's not. So I want to go with what it says on the board, or on your sheet. So number one, it says divide the equation into oxidation and reduction half reactions. Now, and in there, in brackets, it says oxen raw and red cat oa. And I know what you are thinking, what does that mean? I assure you in a minute, that will make sense. Okay? Now, the first part about that is knowing how you find your half reactions. So what you've got to do is you've got to figure out which element is going through oxidation and which element is going through reduction so you can break it in its two halves. That's the first most important thing, and that's what we did yesterday, is we went through reactions and we said, okay, what's going through reduction, what's going through oxidation? That's your first thing you have to be able to identify, and that's not even on here. That's the minimum expectation for you to be able to do this. All right, number two. And again, we're already in our half reactions. It says balance all the elements besides who? Hydrogen, oxygen. And this is a little funny saying that I always say, but again, what says in here goes apparently to the entire world according to this video. But what I always say is here is save the H's and O's for last. Or you can say the rest of that. Okay? You get it. Put the letters together. Okay? Number three. Balance oxygens, and this is the important part. So we save the H's and O's for last. Then we're going to look at balancing oxygens. And how do we balance oxygens? By adding waters to where? The opposite side of each equation. Do you always have to add oxygen to every reaction? No, only if what is present? Oxygen. The only reason you add a water is if you've got an oxygen you need to balance. And again, I know that this is kind of like, I don't understand what you're saying. We will get to plenty examples of these. Number four, balance the H's by adding what? Hydrogen ions. This is my fault. I forgot to add this. Yes, I have no idea. I forgot to add this in. So do me a favor. Underline the H plus ions. Underline those two things. And then right above it, there's some space. Write the word in an acidic solution. And solution is just S-O-L-N. In an acidic solution. Yes, sir. Go ahead. So basically, if the hydrogen is on the reactant side, you add the hydrogen. If the H is on the left, you add the H pluses to the right. So you keep it balanced. Okay? So again, you only add H pluses in what type of solution? In an acidic solution. Okay? All right, number five. Balance the charge by adding what? Electrons. And that, again, I know that sounds weird, but we'll talk about this. And here's a little memory trick. If it's the oxidation half, the electrons go on which side? The other side. And when I say other, what do I mean by the other side? The product side. So if you want to write the word product underneath that, I would write that. And here's why. Keep reading. Reduction, the electrons go on the what side? Reactant side. What's the opposite or the other side from reactant? The product. Now again, I just used OO for mnemonic there. So oxidation goes on the other side. Reduction goes on the reactant side. And will always be that way. Okay, number six. Multiply the half reactions to make the number of, and again, this is where it's kind of weird, but it will make sense later, the number of moles of electrons equal. So here's what you're going to find. The LCM. What is that? Least common multiple. It sounds more complicated than it is, but I assure you it's probably the easiest part of the entire process. Okay? Okay? The reason we need to do this, we're going to make the electrons equal for what? And that's in orange. For both half reactions. So for the oxidation half, you'll have a number of electrons, and the reduction half must have the exact same number of electrons. And why do we want to do that? What does that say? So, very good. So we can cancel out all the electrons and balance the charge. All right, step number 7. Cancel out any common terms on opposite sides and recombine the two half reactions. That'll make sense later. Okay? Now, number 8, I'm going to pause that. I don't want to get into that today. We'll look at that a little bit later. But what do you do if you're in a basic solution? We'll talk about that later. I don't want to get into that today. I want you to be able to do 1 through 7 first. And then finally, step number 9 is what I call the ace. It's the ace in the hole. Okay, the ace in the hole is what you make sure you do at the very end. You check the balance of the atoms, the charge, and the electrons. The ace in the hole. Does that make sense? So balance, check that at the very end, check the atoms, check the charge, and check the electrons and make sure everything cancels out. So let's look at an example of how to perform this. Guys, in your notes, I'm scrolling through all this stuff. This is your rules for oxidation numbers. Like I said, I need to rearrange this PowerPoint just to grunt. So it goes through how to solve for oxidation numbers, which I expect you to know how to do by this point. Okay. I do want to pause here. This is something that's in your notes, but you've all, I think, figured it out yesterday, is that if we're talking about metals, do they normally oxidize or do they normally reduce? And remember, we said that oxidation is a loss. Well, why would metals want to lose their electrons? Okay. Very good. Group 1 and 2 have 1 and 2 valence. Well, what do they want to do with those two things? They want to get rid of them. Okay, so when you lose, that's oil. That's oxidation. Okay, now remember, what did I tell you guys about reducing and oxidizing agents? You don't have to worry about those anymore. Okay, they're opposite, but you're not going to be tested on that. So remember, easily oxidized, this is our oil. Okay, now, why would nonmetals want to gain electrons? Very good. So to fill their valence. Okay? And what do we call things that gain electrons? They are reduced. They are rigged. So we've got some things oiling and we've got some things rigging. Does this mentally make sense now? Okay? All right. I'm just going to kind of bypass this. I've never really talked about that. It's really way more in depth than it needs to be. But that makes sense. All right, so before we get into our half, matter of fact, we've already done this, haven't we? Well, we've done aluminum plus I2 yields AlI3. We've already done this one. Okay? Can I show you something really weird? Look in the picture way down here at the bottom. Look at that right there. You're right, it doesn't make any sense, does it? How? Okay, here's what's weird. AlI3 or Al2I6. It is the same thing. What do we call things that are most reduced forms? Empirical formula. Okay, so this is really, in a strange way, it's really your ionic MF, as bad as it sounds. Okay, because normally when we talk about molecular and empirical formulas, we're talking about covalent bonds. Well, what's aluminum and iodine? Ionic. So really, if you kind of looked at it under a microscope, this form is actually more stable. So this is better in terms of a solid compound than this one. So sometimes it will oddly, weirdly, strangely make that more of a compound. Dustin? It's the weight bonds. It's the weight bonds. No, because it balances on the other side. Mary Beth, you good? Okay. All right. I just wanted to show that to you. That sometimes it's a little odd how it works. All right. We've done this one, right? Yeah, we've done this one. Okay. I want to get to half reactions. Hold on. Stay with me for just a second. All right, perfect. So let's do one more thing. So right here, before we get into half reactions, it says not all reactions are redox reactions. Again, if you have reduction, what else must occur? Oxidation. So let's look at this example. It says reactions in which there has been no change in oxidation number are not redox reactions. Remember, there's two ways you can tell if a redox reaction has occurred. The thing you look at is look at the state of matter and then look at the oxidation number, okay, and see if it changes. So our first example is we've got silver nitrate plus sodium chloride. Notice what happens to all of the elements. So silver from the reactants to the products, did it change or stay the same? Stay the same. Nitrogen from the reactants to the products did what? Stayed the same. Oxygen from the reactants to the products stayed the same, and then sodium from reactants to products stayed the same, and chlorine also stayed the same, right? So do you agree that just because it was a double replacement reaction does not automatically make it a redox? Okay, I will tell you this. If you want to add this somewhere to your, and you don't have to write all this down. Don't worry about all this. I will tell you that all single replacements are always redox. You may want to jot that down. All single replacements are always redox. As a matter of fact, you can add another thing to that. All single replacement and combustion reactions are always redox. So whenever you see a single replacement or a combustion, it will always be a redox reaction. And the reason why, and I'll pause and I'll let you think for just a second. All single replacement and combustion are redox. Yes, sir. Yes. Very good. Very good. Very good. So on the reactant side, one thing is in its elemental by itself state, and then it's going to react, and it's going to change its oxidation state. Combustion. What do you have to combust? Oxygen. And so it's going to create an oxidized form of whatever it's combusting. So if you have a hydrocarbon, which is CH something, right? When oxygen reacts, do you agree you get carbon dioxide? The oxygen went from elemental to carbon dioxide, so it changed as well. All right, so go ahead. This? Don't worry about all that. Okay? These are the rules. Again, this is what you have in front of you. Again, I've changed, edited, added just a smidge. Yesterday before I printed this out, I went in and read it one more time, and I made a few additional changes. So this is in your notes, but I would prefer you to use the one that's on the half sheet. Okay? So let's look at our first one. So let's just follow the steps. The first thing it says divide the equation into oxidation and reduction half reactions. Before we can even divide them in half, we've got to determine which species is going through oxidation and which species is going through reduction. The first rule, okay? First rule, and we've already said this. Matter of fact, you guys write it up here. First rule is find the zeros. That makes it so much easier. Find the zeros. And what do I mean by zeros? The ones that are in their oxidation state of zero. Are there any species? Now I keep saying the word species. What do I mean? Which element, which ion, which compound? And the reason I say species is because that's how you're going to see it on the test. Like a lot of questions say species. Are there any species that are zeros on the reactant side? No. Are there any species that are zeros on the product side? Which one? Say it again. Both of them. Very good. No, it's not, but we'll take care of that in a minute. That's what the half reactions are for. Okay? Everybody good so far? Now we've got to determine which one goes through what. Step 2, again, so second rule, and again, you can write this up top. Second rule is find reduction. Find the reduction. Which species reduced and how can you tell? Chromium. How do you know it reduced? Because 3 positive to 0 is going down. So that is your reduction path. Would you agree with that? That's his oxidation number. Okay. Now, that automatically leaves what to be oxidized? Chlorine. Would you agree or disagree that it does, in fact, go up in charge? It goes from what to what? -1 to 0. All right. So we've done part 1. We've established what went through oxidation and what went through reduction. Now we can set up our half reactions. So do this with me. I'll do it. No, I want all the different colors. All right, so help me out. It's Cr3 plus Cl minus goes to Cr plus O2, right? No, Cl2. Thank you. Why did I say O2? Thank you. All right, so this is where you know how I shorthand everything? This is one of my shorthands, but I can assure you, I don't see it anywhere else, but it works, and it is flawless if you will commit to it. This is a part of the things that you guys just have to suck it up and do it my way because it makes it a lot easier. Okay? So write it like this. Leave a little space, and I promise you I'm going to explain it. Okay? I promise I'm going to explain it. Rxn and Red Cat OA. It's a mnemonic device that will help you figure it out. Because here's what I'm doing for you. I'm building a system that when you write these half reactions and you're going to learn what some of the follow-up questions are going to be, guess what you don't have to do? You don't have to think. You just look, and it tells you. And again, you will understand what I mean when you see the questions come your way. So let's talk about what this stands for. What does Rxn and Red Cat OA mean? What do you think Ox stands for? Very good. So I'm just going to write this in. You don't have to write this in if you don't want to. It's totally up to you. If you know what AN stands for, you get a high five. What did you say? What'd you say? Dustin? What'd you say? Anion? Okay. Not anion. It is actually anode. Again, he just said it. Again, these are things you don't know yet. But okay. It is anode. I'll explain that in a minute. Does anyone know what they think RA stands for? It's something you will never be asked about on the AP exam. Reducing agent. Now, here's the reason that I still include that in my setup. When I first devised this 6 years ago, the reducing agent and oxidizing agent were still a part of the test. Okay? They still asked, what species is the oxidizing agent? Which species is the reducing agent? So when I built this, I said, you know what? And when I found out they took them off the test, I said, I'm still going to teach it this way. Here's why. In case for some freak reason you come across a question that asks about that specifically, you still can figure it out because I left this in the little mnemonic device. So if you ever get to college and need it, it's already built in for you. Okay? Now let's jump down to the other one. What do you think that red stands for? Very good. Reduction. I always get that. I always hear people say cathode. It's not cathode, it's cathode. Cathode. Okay, anode and cathode. Okay. We're going to talk about anode and cathode when we get to electrochem, and that's why this is important, that you're already seeing the setup. You're already seeing the foundations of what it is. And now, obviously, what do you think OA stands for? oxidizing agent. Okay. Again, I'm almost positive you're never going to see the reducing agent or oxidizing agent questions, but it's there if you ever need it. All right, so let's go ahead and set it up. So we've got our half reactions. You already told me that chromium went through which setup? Or went through which half? Went through reduction. So here's what we're going to do. We're going to write it in half. So we're going to say Cr3 plus going to Cr. And the first time everyone sees this, you're like, this is stupid, this is dumb, this is awful. But by the time you get to the end of doing all these in electrochem, they're actually kind of fun. They challenge you, but they're kind of fun to do. It's like a puzzle. All right? Now, what is the oxidation half? Chlorine going to Cl2. Okay? So do you agree we've split them into our two halves? Chlorine ion oxidized into chlorine gas. Would you agree with that statement? Chromium ion reduced into chromium metal. Would you agree with that statement? That's what we've got set up. So we've done step number 1. Okay? Let's look at step number 2. And again, guys, let me just go ahead and say this. Do you agree that even though you have the Lewis structure steps, even though you have the oxidation number steps, do you agree eventually you won't need this? Eventually, you will get to the habitual part where you'll just run right through it. I promise. Okay? All right, so step number 2. It says balance all elements besides who? The H's and O's. So let's look at our first one. I've got one Cl and 2 Cl. So what do? 2 in front of which side? The left side. So are my chlorines balanced? Okay? Let's look down there at chromium. I've got 1 chromium, 1 chromium. So what's happening? I'm good. Does that make sense? It doesn't? It doesn't? Okay. So we're done with number 2. Number 3, balance oxygens. I'm going to stop right there. Do I even need that step? Why? There aren't any. Right on. Number 4, balance H's. Keep right on trucking. Number 5, balance the charge. All right, so let's stop there. Do I have a charge issue? Yes. And it says balance the charge by doing what? Electrons. And this is where this other little memory trick comes into play. It says balance the charge by adding electrons. The oxidation, the electrons go on which side? The other. Now when I say other, what am I talking about? The product. So let's think about this. Currently, what is my charge on the reactant side of the chlorine? 2. Negative 2. So how many electrons do I need to add to the product side to make that balance? Very good. So let's add 2 electrons. You with me? Because the charge over here is negative 2, and the Cl2 is negative. Is neutral. You with me? Okay. All right. Let's go to the next half. I've got a positive 3 on the reactants and a neutral on the right, on the product side. This is where everyone kind of gets thrown off a little bit here. Again, what am I adding? I'm adding electrons. So according to the little sheet, it says reduction, the electrons going on which side? The reactant side. So I think you get it, but how do I make this entire reaction have the same charge on both sides? Okay, I need 3 electrons on the reactant side. Wow, that's really bad. Thank you. I was writing the plus sign too soon. So logically, have I lost anyone yet? Okay, we've balanced our atoms. Now we've balanced our charge, correct? Yes, no, maybe? All right, this is the part where everyone's kind of like, okay, I get it, it makes sense, but I might possibly forget this. This is the part you cannot forget, and this is what's so important. So look at step number 6. Multiply the half reactions to make the number of what equal? Of electrons. That word moles of electrons will come into play a lot later on. Do me a favor. In fact, where it says moles of electron, do as I do. So, again, I know it says the whole word, do me a favor. Circle it on your sheet like this and write N equals. No. R is a gas and energy constant, right? P is a pressure. V is volume. T is temperature. N is number of moles. Okay? Now, we'll talk about something later when this N comes into play. Again, I promise we'll come into it a little bit later on. Do y'all want to see the formula? You want me to go ahead and just one quick thing? Hold on. Nope, that's wrong. Nope. You'll see this in electrode. Delta G. Do you remember what delta G was? Gibbs free energy is equal to negative N. And N would be number of moles of electrons. If you don't know, I'm going to say it. Some of you are like, oh, I've heard that. It's called Faraday's constant. Okay? Okay? And then, do y'all remember what that curly Q looking E is? Cell potential is the voltage. Okay? All right. Again, we're not going to worry about that. I just want to go ahead and, I promise you we'll get there. Oop, wrong button. So let's go back. So the problem is when we see this, we said we multiply the half reactions to make the number of moles of electrons equal for both halves. The reason why is we want to cancel out all the electrons and balance the charge. I told you this is the part where you're going to have to find the lowest common multiple. What is the least common multiple between 2 electrons and 3 electrons? 6. Amazing how that 2, 3, 6 rule just comes into play, right? Again, this is a part where you just got to commit to the methodology of how I do this. It's about a process. It is. So, if I've got a 2, what do I give it? A 3. If I've got a 3, what do I give it? A 2. I'm multiplying through the entire equation. No, I'm done adding stuff. I just made them even because I'm a nerd. It is called OCD. Shut up. All right. So, I actually left a step out. All right, what did I do? All right, which part? What I'm trying to do is I'm trying to make this number and this number be the exact same. And the reason why it says because we need to cancel out all the electrons. So right now I can't, but when I do that I can. All right, so here's what I got to do. This is the last step on this part. What we've got to do is we've got to recombine these formulas with the distribution of the number. Okay? Now, here's the most, and I'm only going to draw this one time. We have to keep them divided on the arrow side. So what's on the reactant side stays where? The reactant side, and the products stay on the product side. Okay? All right. Now, this is where you got to really dig deep and think. Do the 3's and the 2's outside the brackets distribute to what's inside? It distributes to everything. So it goes here, and it goes here. All the while, the 2 goes here, 2 goes here, and the 2 goes here. So let's start with the top, and I'll always just go back to the top and start. I'm going to start on the reactant side. So I've got 2 Cl minuses, but I've got to distribute that 3. So what does it turn into? 6 Cl minuses. Do I have anything else in the top half on the reactant side? So where do you go now? Go down to the next half. Now, this is where it should make sense, but you just have to hear me to say it. What was the whole purpose of multiplying by the 3 and the 2? To get rid of these. So do I need to even write them? Have you ever seen a balanced chemical equation with electrons written in it? And you never will. So do I need to write these 6 electrons down? Eliminate them. That's the whole purpose of the brackets. That's the whole reason we did it. So let's eliminate. So we're just going to move on from those. Now, do I have anything else on my reactant side? Be careful. What do you have specifically remaining? 2 chromium 3 ions. Does that make sense? What's wrong? Okay. I distributed from out here. Again, that's one of the hardest things for people to remember is the distribution of everything. You just have to do it enough to get it in your yes. Okay. Am I finished with my entire reactant side? Yes. All right. So now we go to the product side. Let's go back to the top. So what do I have on the product side of my oxidation half? How many Cl2s? I've got 3 Cl2s. Does that make sense? No. It's a diatomic. Okay? No, sir, it's the ion. Okay? Now, I've got electrons again. What do I do with those electrons? Get rid of them. I don't need them. Am I out of products on the top half? Let's go to the bottom half and be very specific. What do I have on the bottom half? Do I have anything left? I'm out. So, here's what I want to do. Let's look at number 7. And I kind of have number 7 worded really weird. And I apologize. Number 7 is actually backwards. Do you see how it reads? Cancel out any common terms on opposite sides and recombine. Technically, it should say recombine and then cancel. So you may want to make a note of to swap those. You recombine and then cancel. That's on me. I apologize. So basically, you need to recombine first and then cancel out any terms. No, we did it right. I just have it worded wrong. Okay. Yeah. All right, so let's look at step number 8. It says step 8 says if in a basic solution. Now look up here at the top in the red word in the very top of this thing. What does it say? So do I even need step 8? Fantastic. So let's go on to step 9. And this is what I call the ace in the hole. We want to check the balance. We want to check the atoms. We want to check the charge. And we want to check the electrons. Okay? So let's look at our chlorines first. How many chlorines on the left? And again, I teach. I've always taught this, and I'm kind of out of room. But I always write. Kind of out of room. If you guys got some room, I'll do it in orange right here. I always write A, C, and E, and I just check them off as I go. Okay. So I've got 6 Cl's on the left, and how many on the right? 6. I've got 2 Cr's on the left, and how many on the right? So do my atoms balance? Yes. Okay. I'm going to go to electrons next because that's the easiest. Did I get my electrons canceled with the same number? How many? I'm just going to write that number 6 down. Okay. That tells me how many electrons I canceled. The charge is the hardest because you really got to think through it. Let's start with the easy side first. Let's look at our product side. Is there any charge on that product side at all? So what is this whole product side? It's neutral. So do you agree that the reactant side must also be neutral? Well, let's look and see if it is. I've got 6 minuses and 3 positives. Does that cancel? So this whole side is neutral, so that checks my charge off. Now do you see why the ace in the hole is important? Okay. We'll talk about that electrochem. Perfect. Yep. Okay. All right. Any questions? Don't worry about it. Okay. Yes, ma'am. Equilibrium. Okay. All right. Let's do one more together, and then I'm going to give you guys a chance to work on one on your own. This is chapter 4. This is solution and reaction stoichiometry. Okay. Again, the first thing we've got to do is we've got to determine what went through reduction and what went through oxidation. The first rule was find your zeros. Dun dun dun. What's wrong? There are none. All right, well, here's what I would do. I would find the things that are the simplest to identify. You guys are smart enough to know to look at the MN and the FEs. Which one's going to be the easiest to identify what went through what? Why the FEs? Because it's not with anything else. You can tell when it went from FE2 plus to FE3 plus. Did FE go up or did it go down? It went up. So is that oxidation or reduction? Up. Up is oxidation. Reduction means it went down. So, yes, no, maybe. Leo says Gur. It's MN what? 4 plus, 7 plus, or 2 plus? All right, so let's set up our ox and raw and red catoa. Ox and raw, red cat oa. Yep. Very good. That's what y'all didn't see yesterday. That's what I kept saying. You don't know what it is yet. Nothing. Don't ask. All right. So, again, you just told me that iron went up, so which half is that? That's your oxidation half, so let's start there. So we've got Fe2 plus going to Fe3 plus. Do I even need to figure out what the Mn did? No, because if one goes through something, what does the other one have to go to? The opposite. It's got to do, yeah, you see what I'm saying? It's got to go through reduction. So I'm going to say MnO4 minus goes to Mn2 plus. Everybody good and understand why these two halves are what they are? Okay? All right, sir. How do you know? You tell me. Did it go up? It went from 2 plus to 3 plus. Is that up or down? You're thinking too hard. Did it go up or did it go down? It went up. That's oxidation. If it had gone down, that's reduction. You with me? Okay? So this is oxidation. Now, the reason we started off with oxidation on this one because it was easier to determine. You could just look at the FEs. It was 2 plus to 3. That's easy. That's up. Okay? Now, rule number 2 is balance everything except the H's and O's. Save the H's and O's for last. So I've got 1 Fe, 1 Fe, 1 Mn, 1 Mn. So am I done with the step 2? Save the H's and O's for last. I'm on with just step 2. It says balance all elements besides hydrogen and oxygen. Alright, so step 3. Balance the oxygens. Now I'm going to pause here. Do I even need this step? Why? I've got an oxygen. And it says you balance them by adding what? Waters. To the opposite side of each equation. Now, which one is the only half I need waters on? Do you agree the reduction half is the only one that needs waters? Because the other one doesn't have any. Okay. Now, here's the most important part. I can come over here and I can be real spiffy and I can add a water. But here's the problem. I'm wrong if I do it that way. What am I missing? Because right here, I've got 4 oxygens. As it's currently written, I only have how many? 1. So how do I make it equal? 4. Pause. Hold that thought. Hold that thought. So do you agree that my O's are balanced? Step 4. Balance the hydrogens. Okay? Now, how do you balance hydrogens? The H plus ion. And where do you add it to? The opposite side. How many hydrogen ions? 8. Very good. So I need to add 8 H pluses. It is. You just have to just get it in motion. All right, step 5. Balance the charge by adding electrons. Let's start with the easy one first. Okay, so I'm going to go ahead and draw my line. Up top, in the oxidation half, first of all, where do the electrons go on the oxidation half? The other side. So I already know it's got to go on the product side. Can anyone tell me how many I need? Why do I need 1? Very good. So if I've got 2 positive and 3 positive, if I add 1 electron to the 3 positive side, does that bring it down to 2 positive? That's why. I would put 1 just for visual confirmation. Okay? Yes. You're looking at the charge, right, Trish? Okay. Now the bottom one's a little bit more challenging. Okay? So let's look at the entire reactant side. I've got 8 positives and 1 negative. So what's the entire charge? I've got positive 7. 8 positives, 1 negative. Okay? Let's look at the product side. I've got 2 positives and nothing. Does that make sense? So it's positive 2. Now again, here's an important question. Do they have to be 0? They just have to be the same. Now, here's the rule. If it's the reduction half, which side do the electrons go on? Reactant side. Very good. So I've got 7, and I've got to get it down to what? How do I get it down to 2? Very good. So we're going to do 5 electrons on that side. Okay? It was 1 and it was 1. You're looking at subscripts when you balance atoms. Okay? All right, step number 6. Multiply the half reactions to make the number of moles of electrons equal for both halves. Well, what's the lowest common multiple between 1 and 5? 5. So really, the only half that I'm messing with this time is which half? The top half. And how many do I mess with it with? Does that make sense? Okay. Does the 5 distribute throughout? Yes. Okay. So step number 7, again, this one's the one that's backwards. Recombine and cancel out. All right, so let's go ahead and recombine. Remember, we're staying on each half. So I'm going to go ahead and drop my arrow in there. So let's start with the oxidation reactants. How many oxidation reactors do I have, and what is it? Okay, so I've got 5 Fe 2 pluses. All right, do I have any more oxidation reactants? Nope, I'm out. All right, my first reduction reactant is electrons. What do I do with it? Get rid of it. I don't need it. Everybody go there? Do I have to distribute anything on this entire bottom half? No, so just write what you see. So 8 H pluses plus MnO4 minus. All I did was just rewrite what I had. Am I out of all of my reactants? All right, let's go to the other side. Let's go back up to the top half. What is my product on my oxidation half? Very good. I've got 5 Fe 3 pluses. Okay, I've got 5 electrons, so I don't need those anymore. And is there anything I need to distribute on the bottom half? Nope, so just write what you got. So plus Mn2 plus 4 waters. Okay, you kind of hate it now, but I promise you it is kind of fun once you figure out how to do it. Hang on, let me finish and I'll answer your questions. So step 7 says recombine the 2 halves and cancel out any common terms. Is there anything that's the same on both sides? No, nothing is the same. So you're done. Move on to step 8. If in a basic solution, now you guys see it. Is it basic or acidic in your reaction? It's acidic, so I don't need that one. And finally, we got the ace in the hole. So ACE. Let's start with the easy one. What are your electrons done? Atoms charge electrons. Okay. How many electrons did we cancel? 5, so I'm just going to write down 5. All right, let's look at atoms. I've got 5 Fe's, 5 Fe's, 8 H's. How many H's on the products? 8. You with me? Does that make sense? All right, I've got 1 Mn, 1 Mn, 4 O's, 4 O's. So my atoms check off. Now, the charge, again, is the most complicated step because you really got to pay attention to it. I'm going to be honest with you. If your atoms balance, there's a high probability your charge does, but just get in a habit of looking. All right, so I've got 10 positives plus 8 more makes it how many? 18 minus 1, so it's what? Positive 17. I know you're thinking, what the hell? Why is that so high? Okay, but it is. It's a lot of atoms. Let's look on the other side. All right, I've got 5 times 3, which is what? Plus 2 more, which is positive 17. So they match. So our charge, they don't have, bingo. That's the hardest thing for students to grasp, is that it doesn't have to be 0, it has to be the same. Any questions? Any questions? Ask now, forever hold your peace. All right, I'm going to let you guys run with the next one. You can add whatever you need on either side, as long as it balances it. Now I'm going to go ahead and tell you real quick. The first thing I want you to do is determine which element went through what to set up your halves. Now I'm going to go ahead and tell you. This was going to be a little, actually, you know, I don't want you guys to do this one. Nope. You know what? I tell you what. You know, if you can do this one, you can do any of them. Yes. Hang on. Hang on. Hang on. Follow the rules. Follow the rules. You can do it. I have faith. Yeah. Okay. So I know that MnO4. This is going to be 7 plus, and this is going to be plus what? This is plus 4, right? So. Ox. Somebody do me a favor. Shut the door, please. Okay. All right. So my manganese is going to be my reduction. So O4 minus MnO2. That leaves me with I minus going to IO3 minus there. All right. So all of my atoms balance. 1I, 1I, 1Mn, 1Mn. The O's are where everything kind of gets into a tailspin. I need 3 O's, so I'll balance it with water. So I need 3 waters. That gives me 6 hydrogens. Okay, so I'm going to go ahead and do the electrons while I'm at it. I've got 1 negative on the left, 1 negative on the right, plus 6. That means I need 6 electrons. Okay, the bottom one is also kind of weird. I've got 4 O's and 2 O's, so that means I just need 2 waters, and that gives me how many hydrogens? 4 hydrogens. Okay, so my electrons, I've got a neutral and I've got positive 3, so that means I need 3 electrons. So now let's look at my electrons. Which side do my electrons the only one that affect? Which half? The bottom half, and what do I multiply the whole bottom by? 2. All right, so that then gives me 3 waters plus I minus plus 4 hydrogens plus MnO4 minus yields IO3 minus plus 6 hydrogens plus 2 Mn. Actually, I forgot my. I've already messed this up, hadn't I? Yep. All right, so let's go back in and let's throw an 8 in there and a 2 in there because I forgot to distribute. MnO2 plus 4 H2O. Now, this is one we haven't done like this yet because do you have the same thing on both sides? Yes. I've got 3 waters here, 4 waters there. When I combine, what does that leave me with? That leaves me with just one water on that side. Now, do I have H's on both sides? Yep, I've got 8 and 6. So which one wins? Okay, so that means I've got 2 left, and those disappear. You have to cancel like terms. That's step. Look at it. That's step number 7. Recombine the 2 half fractions and cancel out any common terms. Because I had water on the left and water on the right. It doesn't matter. They're the same compound. So all of those go away, and I'm only left with 1. Over here, I had 8 hydrogens and 6 hydrogens. Well, the 6 disappear, and I'm left with 2 there. No, there's 2 on the left, none on the right. Yep. Yes. Yes. Yeah, it still balances. Because it's just like math class. You can't have 2 x's. You can't have an x on each side and a y on each side. You have to combine like terms. It doesn't matter. You can only have one compound on the same side.